we talk about quantum electrodynamics, or also known as QED amongst physicists. And we'll only do tree-level diagrams for this course. In late November and early December, I will give 2 supplementary lectures which will treat one-loop phenomena and computation of beta functions. Those of you who came to yesterday's colloquium, you heard a lot about beta functions, and you will learn what beta functions are in QFT2 and also in the supplementary lecture, the set of supplementary lectures I'll give you. So QED is kind of the crown jewel of quantum field theory. A lot of the modern ideas about quantum field theory were developed in the context of QED. It's also one of the quantum field theories that we think are valid up to the energy scales that we have experimented so far. So, as usual, we start with the classical Lagrangian for QED. Now, as you know, this is a theory of electrons, and we'll also include muons later on today, interacting with each other via photon exchange. And this is the interaction term. And let me remind you what the Dirac-Lagrangian is. And the electromagnetic Lagrangian is and the interaction Lagrangian. Recall that yesterday we saw that an electromagnetic theory consistently couples to a current that is conserved. So we know of such a current, and that current for electrons and positrons is just this thing. And we know this is conserved. E is some positive constant, which is the absolute value of the charge of the electron. So this is our coupling constant. Now we couple the current for the electrons to our electromagnetic field via this sort of coupling. Now, we see that this theory, okay, before I move on to discussing properties of the Lagrangian, let me make a comment about, when you quantize, you need to fix the gauge. So we are going to write down the photon propagator today for Feynman diagrams. So we use this gauge fixing term. Now, one question that I didn't address yesterday is that since the gauge degrees of freedom or the gauge invariance is more of a redundancy of description, right? It's not really a symmetry. It is. We have a responsibility to show that whatever results we derive is not dependent on gauge. So the physics is independent of gauge. And I'm not going to do that in this course. It's much more efficiently and elegantly done in the path integral formulation. And in the next course, you will actually see how the gauge choice is something that does not affect the physics. Yeah?
suppose like that. Should be there. You ask them using Einstein.
Thank you. Okay? So, the fact that this theory is the physical results do not depend on gauge is something that will be proved in QFT2 course. And it's done very elegantly in the path integral formulation. Okay, now let's come back to our Lagrangian here. We saw that under gauge transformation, this thing was invariant, but now our interaction Lagrangian has in it an A mu explicitly. Therefore, have we given up gauge invariance? We cannot give up gauge invariance because gauge symmetry is not a symmetry. It's a redundancy of description. And if our theory is dependent on our description, then it's kind of a contradiction. So what happens here is that, recall that this Lagrangian had a global phase symmetry, which is related to the conserved current, which we call the electric current. And if this was the only symmetry of this Lagrangian, if this was the only allowed transformation for psi and psi bar under phase transformation, then it is true that if we then now do a gauge transformation, this term will change to something else. It will pick up an extra term, and our whole Lagrangian is not going to be invariant. So to get around this, what we do is that we allow these transformations to become local. So we take a global symmetry and we allow it to become local. And this is sometimes called gauging a symmetry. And when you do that, what you do is you take psi of x and you replace it by a new psi prime, which is, now I'm going to introduce a constant here, e, for convenience. And now instead of the parameter of transformation being a global parameter that is independent of space-time point, I'm allowing it to be a local parameter. So similarly, so when we do this, we see that, like in the global case, the mass term of the Dirac-Lagrangian is still invariant because we got psi bar and psi, but the derivative term is no longer invariant. And that's because the derivative now not only just acts on this guy, it also acts on this guy. So the derivative term in our Lagrangian is picks up a new contribution, which is the derivative of this alpha function, and the other term as before. So now if we do simultaneously a gauge transformation such that we choose the function with which we do the gauge transformation to be the same function alpha, then our interaction Hamiltonian, Lagrangian, picks out this new term. And this is precisely the term that the kinetic term picked out. So those two guys cancel out. Okay? So we see now what we are calling a gauge transformation is not just this transformation, but when we make a gauge transformation of this whole theory, we must include this transformation as well. It's only the combined transformation that keeps our theory invariant. Okay? So this is our new definition of a gauge transformation. So the comment I want to make now is that our global phase transformation, where we just changed, there could be an E here. This is still a symmetry, right? Because it does not touch the terms which involve A mu and F mu nu. So our theory still, because of this global phase transformation, we still have a conserved charge because we can apply Noether's theorem. But in addition to this symmetry, when we do a gauge symmetry on the A, we must also allow alpha to become local. So this is gauging a symmetry so suppose you have some Lagrangian with a global symmetry and you can allow it to become local. And that's typically what that happens is that it forces you, if you want your Lagrangian to remain invariant, it forces you to introduce some sort of interaction. Okay? And this is a trick by which you can find some consistent interaction for a Lagrangian which has a global symmetry. It doesn't always work, but this is a kind of a fun and an interesting trick. Okay.
Is there something like, I don't know, just curiosity, or if we have a Lagrangian with like rescaling, like a form of symmetry, and we make it local depending on the point, is there any theory with that that gives rise to an interaction?
So you've been gauging a conformal symmetry, right?
Yeah.
Not that I know of. I mean, there are theories which have a local conformal invariance, but I'm sure there is some kind of in yesterday's talk, Jaume Gomez talked about how sometimes if you have Poincare symmetry plus a scale invariance, just a scaling invariance, a lot of times, in nature it seems that most of the cone of field theory you see, it actually becomes like it's expanded to a conformal group, right? And in 2 dimensions, the conformal group is infinite, and in the case of string theory, that symmetry is actually a gauge symmetry. But I can't see how you can get that by gauging some symmetry that was already there. So.
Yeah, I was wondering if you want to make your Lagrangian gauge invariant, can you introduce a different transformation which doesn't come from symmetry? Like you say you gauge some global symmetry or
right.
global, but is it necessarily the case that it originates from some?
No, it doesn't have to be. I mean, I cannot think of let me think of an example where that is the case. So so for example, you can actually reformulate GR as a gauge theory, and then you can couple that to matter sector. But even then, I think you can think of it as gauging the Poincaré symmetry. So, but it doesn't have to be. I mean, the gauging the symmetry trick is kind of an arbitrary trick which seems to work in this case, and it also seemed to work in the case of the Yang-Mills field. Because the way that you'll see, if you go and read the paper by Yang and Mills, which is extremely readable, you'll see that the way that they derived Yang-Mills theory is by saying, oh, what if we have a Lagrangian with a global non-abelian global symmetry, and then what if we gauge that? Then what kind of interaction we would have to introduce? So it's a way of, it's really a trick rather than a well-defined procedure. I mean, I've read other interpretations, like possible geometric interpretations, like underlying geometric interpretations of gauging a symmetry, but I'm not convinced, so I'm not going to give those to you. Okay, so let me give you another example of a gauge theory, and that is scalar QED. So the scalar QED is, you have some, complex scalar field, and you have the electromagnetic Lagrangian, and you have some interaction term. And you can show that this has a gauge symmetry. So this is our usual complex scalar Lagrangian. And we have our electromagnetic field. And the interaction Lagrangian, in this case, it's the usual conserved Klein-Gordon current, which is famously not positive and therefore didn't work as a quantum mechanical probability current. So this is our Klein-Gordon current, which is conserved. And this total Lagrangian is invariant under phi let's put an E here. So perhaps the real geometric interpretation of gauging the symmetry is that it motivates us to write these interaction terms in a much more elegant form, which has some geometric, which has a geometric interpretation. So if we introduce a new derivative, which is called a covariant derivative. So for, say, QED, we define it in this way. Then under the gauge transformation, so under gauge transformation, this object has a nice transformation property. Right? And you can, so then we can express our QED Lagrangian as D slash of this new operator plus LEM. So this is called the covariant derivative. Similarly, for scalar QED, if you define a new covariant derivative in this way, yeah. So what is wrong with my equation there? Can someone tell me? There should be a side here, right?
Yeah, it seems.
Yeah?
Yeah.
Right, so if you allow this, then our scalar QED Lagrangian also takes a very simple form. So you've met another covariant derivative earlier in one of the Psi courses, which was in GR, right? And this is analogous. So in GR, what you had is that you had a covariant derivative acting on, say, some vector like this, and under some coordinate transformation, this changed in a way which was homogeneous. So your GR lecture may have motivated this by saying, first, by showing that if you just took a partial derivative on a curved space-time or any arbitrary coordinate system, even on flat space-time, if you do some arbitrary coordinate transformation, then the partial derivative acting on some vector does not transform in a homogeneous way. It'll pick up an inhomogeneous term. And in the covariant derivative, you introduce a potential, which is analogous to our gauge potential here. It's called the Christoffel connection, or the metric connection, which also transforms inhomogeneously under coordinate transformation. So the two inhomogeneous term from this guy, they cancel out, so that the total transformation is something homogeneous. So this is completely analogous to this, and that's why this is also called a covariant derivative. Yeah?
But is A mu a true connection in a mathematical sense?
Yes, it is. You have to, the physical interpretation of the different connections are different. I mean, but yeah, you'd have to use the language of fiber bundle to show that yes, it is a connection that it is exactly a connection in the mathematical sense. Okay. And as you know, that this thing has an interpretation of holonomy. meaning that if you take a small vector and parallelly propagate it around some small loop, it doesn't come back to itself. And that can be that monodromy, or not being able to come back to itself, is something that is measured by the commutator of the covariant derivative, and on the right hand, what happens is that it measures the curvature, local curvature that is contained in that little loop. If you take a covariant derivative in QED and compute this thing acting on psi, you get something like this. So in that geometric sense, the electromagnetic field strength is a curvature. But it's not curvature in space-time. It's curvature on some more abstract quantity living, on space-time. Okay. All right. So this is our introduction to classical QED. Now we'll move on to the Feynman rules for QED. Now, before we do that, let me just recap some stuff. One thing that we learned from the tutorial, and in the tutorial, what we learned was that if you have a fermion loop in some Feynman diagram, then for each fermion loop, you introduce in your fermion diagram, your Feynman diagram, a momentum integral. So suppose this was, say, P, and this was P going out. But the momentum here would be, say, K plus P, and this would be minus K. And this momentum is not determined by the external momentum. When an external momentum is not determined, you have to introduce an integral over. When an internal momentum is not determined by the external momentum, you have to introduce an integral over K. And because it's a fermion loop, you have to introduce a minus sign. And then for each of these propagator, say, suppose, so we will, sorry, no, that's not what I meant. So we did scalar QED, right? Yukawa, right? So our external states were scalar particles, right? Yeah. So right. So for this thing, we have to we have two propagators, and the propagators do not have any, they should not have any hanging spinor index, because otherwise your matrix element would have would be a matrix in spinor space, which is not what you want. So there should be a trace over the spinor index of the propagator, right? So this was the optional question in the last tutorial. Okay, now let us. What are the additional Feynman rules we get for QED? One is, so for each interaction vertex, for each interaction vertex between like, let's say, two fermions, And they could be antifermions as well. And a photon. So it'll look something like this. We have some fermion coming in. So this is just a this is a fermion. This could be an antifermion or fermion. So the interpretation whether this is a fermion or antifermion, or whether this is a fermion or antifermion, will depend on which direction time is flowing, right? And this wiggly line is what we call is a photon. So for each of these vertex, we write a vertex factor like this, and the photon will have some space-time vector index that it carries. So this is our first Feynman rule. And then for some photon propagator, you'll see that we have to decorate the points, the endpoints of a photon propagator by a space-time index mu and nu. So this is for the photon propagator. And this is in the Lorentz gauge. This has this form. And this is something that we just derived in analogy with scalar field theory, because in the Lorentz gauge, the equations of motion, Maxwell's equation just look like a set of scalar equation for a scalar field without masses. So for an incoming photon, with some polarization, okay, let me just write it like that. So the photon is coming in with some momentum p. We write for that a polarization vector like that, and right. And for an outgoing photon, we have E star of mu, where this mu is the mu that decorates this vertex, which comes from, this Feynman rule. Okay, with these are very simple. A lot of times, what we'll assume is that we will assume that our photons are polarized in a way which is the polarization is real. Then epsilon, epsilon star would both be real, so we wouldn't have to worry about writing star over there. So armed with these Feynman rules, we can now do write down the amplitude for our first QED process. It's called the electron-positron. It's electron-positron scattering. That's what we'll look at. It's also known as Baba scattering. And the cross-section that is that you get from this scattering is what you would have to you'll have to compute for your last homework. So I'm doing half of the work for you guys here. So the idea is that some electron comes in and a positron comes in. They scatter. And in the end, you produce another electron or a positron. So an electron comes in like this. A positron goes out. An electron is going out. A positron is going out. Remember, time is flowing in that way. So now, using that vertex, we have to add up these external lines. So before we do that, let's decorate the external states with the momentum and spin labels. So how can we do this? Can somebody tell me? What can I join? Which
Well, we could join 2.
Yeah, which two? Which two?
The first 2.
Okay, so I can join here and
A photon.
okay, photon.
And then finish the.
Okay, so that's the one diagram. Is there any more diagram? Anyone else?
Okay.
Sorry.
You connect both at all.
Okay, I can connect this thing with this thing. And this thing with this thing, right? So PS, P prime, S prime, KR, K prime, R prime. Okay, good. So let's put a mu here. The photon will carry some momentum P plus K. And say mu here. We could have done the other way around here because nobody's, these are internal labels. The momentum that is carried in this direction is P minus P prime. And now let's write down its amplitude using Feynman rules. Okay, I'm not going to do this. You're going to tell me what to do. All right. What do I do? Someone. Let's take the first diagram. What's the first thing we should do?
Okay, so we have one vertex.
Sorry?
Start with.
So we have.
Okay. You answer a lot of questions. Let's ask. Yeah.
Sorry.
Yeah.
Yeah, I would start with the.
Okay.
You wanna work backward in the flow of arrow, right?
Okay. So let's take an arrow.
Yeah.
Which one do you want to take?
The
First one.
P prime, yeah, the P prime electron.
Okay. So P prime,
That
and
would
then
be, that'd be a U bar, now coming for prime.
U bar, S prime, P prime. Yeah. And then we hit a
Here's
vertex.
the vertex, so you throw in a minus I E gamma matrix.
Okay. That's good.
Then contract it with the photon propagator. So the mu is going to contract with the.
Right.
Oh,
Let's finish our. I suggest you can do that, but
okay.
you're going to get a grammatically incorrect, a syntactically incorrect result.
That's true.
Because the photon propagator has different indices, so you can put it there if you want. But
No, that's right. I should finish the line.
let's finish the line. You know, in principle, you can do that too. Sorry,
So I guess I would do V. It's just V, right? Outgoing antiparticle is just V.
okay. V,
P prime S prime.
R prime,
Sorry, R prime.
K prime, right? So, okay. So
Yeah.
right, so that's one. And does everyone agree with this? Yeah, okay, and then what we do?
Then the propagator.
Okay, the propagator is minus eta. What do we do here?
Mu.
Mu and?
Well,
And then
we should have put it mu. Well, yeah. If we want to be correct
Well,
in the
it's-
picture, we should have put 2.
Yeah, but it's symmetric, so it doesn't matter, right?
Yeah, sure.
Yeah, so, okay, and then
The denominator,
what is the denominator?
p squared plus I epsilon.
What is p squared here?
Oh, k plus b.
P plus k or k plus p squared plus I epsilon, right? And then we get to the other fermion line, right? And the other fermion line similarly is we start with first we start with an incoming antifermion, so we write a V bar for that, R of k, and then minus IE, say gamma, so that should have been a gamma nu, right?
Yeah. That's what I
And
meant.
this is a gamma mu. And then we have an incoming fermion or electron, and this is what we get. All right, good. So this is our first diagram. Because of Fermi statistics, you can show that the second diagram has a minus sign attached to it. And then we can do similarly u bar s prime p prime minus IE gamma mu minus eta mu nu p minus p prime. Now I've forgotten the v factor. So we can note, so that was outgoing electron, then mu, and incoming. Right. Incoming electron, right? So there should be an U here. And I forgot this factor in the notes, guys, so correct that. And then eta mu nu p minus p prime squared plus I epsilon. And then we have this guy, which is an outgoing. Nobody's corrected me. I made a terrible mistake. So we have an incoming fermion, antifermion. So we have a V bar, R of k, and a vertex. We already used mu, so this should be mu. And then we have an outgoing fermion, antifermion. So we have VR prime, k prime. Okay, easy peasy, right? Okay, let's do another one. And let's change our model a little bit for this next one. So I think Akim Kempf gives a whole course on that topic called Quantum Field Theory and Kerr Spacetime. It's a course that is combined course between Waterloo and PI. Yeah, but I think everything is on PERSA. So yeah, that's a good place to. And now these days there are lots of books on this topic. So it's a very important topic because of cosmology. Because in CMB, you actually have to deal with how particles are produced in an expanding universe. So it is a very important topic, but it's outside the scope of this lecture. The question was, would this go through if I replace the space-time metric by some arbitrary curve metric? Okay, so our next example is drawn from QED, which involves two species of fermions. So we are going to do an example where an electron and a positron scatters. Well, they annihilate, and the pair create a muon and antimuon. So the Lagrangian for this has a Dirac part, which describes the electron. So this is the electron Lagrangian. It has another Dirac part which describes a muon field. I'm going to write. And each species of fermion couples to electromagnetism in its own way. Yeah. And this is not a space-time index. It means it's the psi for muon, the field for muon. So here you see that the muons and the electrons don't talk to each other directly, meaning that there is no direct coupling terms between them. But both of them couple to a photon. So the Feynman diagrams would be very similar to this, except that the outgoing states would now be not electrons, but muons. But because there is no direct coupling between the muon and the electron, one of these diagrams will no longer be there. Which one? The first one? Okay. Bets.
Are we doing electron-electron?
We are doing electron-electron scattering to muon-muon. Second one will no longer be there. Good. Because the second one would then have a coupling between an electron and a muon. So our Feynman diagram would be this way. It's an electron coming in, a positron coming in. Now, in my notes, I use different color for the muon, but it's not necessary. Because if you are careful, things will not actually mix. The spinor wave functions. Hang on. Sorry?
Your notes been uploaded? I don't see them.
A what?
So lecture notes 13, right?
Yes.
Have they been uploaded?
But they've been emailed.
Oh. Yeah.
Right? I don't think I uploaded them, but I emailed them. All right, so what is amplitude? Well, we already know what the amplitude is, but instead now, this guy, it's the same amplitude, but now these spinor wave functions are muon wave functions. And you can put some primes on it and stuff like that to make sure that it's not the same thing, but it doesn't really matter, because if you're careful, they will not actually mix. Okay, so let me write that out again. But now I'm writing in a different order. First writing the electron part. So this is the electron-positron part. And then we have a photon propagator. And then we have a muon part. Right. So this is the mu plus mu minus part. Okay. So in a typical experiment, in scattering experiment, our detectors are not so sophisticated that they can pick up the final states of final spin polarizations or of a muon or an electron. Is your question, Fiona?
Should that be a V?
We have
That E and U are they?
Oh yeah, you're right. Yes. So
Should be.
yes. Yep. So this is
Think of the
this is correct. This is. Yeah, I made a mistake in my notes. So propagated,
thank you.
just like a photon. So okay, in our detectors are usually not sensitive to spin polarizations of the final states. Stuff. So when we are doing this observation, what we are going to do is that we are going to sum over the final spin states. Also, the way that usually these beams of electrons and positrons are produced, they are not polarized beams. So we're going to average over the initial spins as well. And these are classical averages and sums, so there is no interaction. So what we do is that we first square this, and we then sum over. So the object that will be entering into our, so this is an S matrix element, but the object that will enter into our differential cross-section or the cross-section, which is what we'll measure, there'll be sum over the spin state. And the 1/4 is because there are two particles whose initial polarizations we are averaging over. And this sum is, I guess this, doing the sum actually simplifies the final result. There may be some detectors, I'm not very sure, which can actually be sensitive to helicities and polarizations. And if you're going to make some experiments in those detectors, then you cannot do this in some, and then you know life becomes a lot more hard in calculating the cross section. Okay, but it can be done. There is actually a whole a very well-defined way of dealing with those things. Okay, so what we are going to have is that there's an E here, there's an E here, so we are going to have 4 factors of E. And because we are taking the mod, there is no minus sign associated with the i's. And then the square of these guys is going to be V bar R of K gamma mu U S of P, and this is U bar S prime P prime, and this is I think I made a mistake. No, I didn't. Okay. there's going to be, now I'm going to use this eta to contract these two gammas. Okay. And this is taking the complex conjugate of this, and then we write the same thing, but not the complex conjugate. So sorry, it's boring, but life as a theoretical physicist is not always very exciting. And then we have the term coming from the photon propagator, p plus k to the power 4. Okay. So this factor is from the muon. This factor is from the muon. Now note that this thing is a scalar. All its spinor indices have been summed over. So it's a scalar in spinor space. This is also a scalar in spinor space. Not only that, even this subfactor is a scalar in spinor space, and this subfactor is also a scalar in spinor space. Same with this, and same with this, right? So what it means is that we can actually move them around, right? They're just numbers. And the other thing to note is that, so these scalars in spinor space, when you complex conjugate them, say V of U R of P, now, complex conjugating a number is the same as taking the Hermitian conjugate of that number, right? Because the transpose of a number is itself. But once we have done this, we can then use the fact that taking the transpose or the Hermitian conjugate changes the order of your matrices if they're multiplied. So I can write this as U R of P dagger, and then there's a gamma mu of dagger. Sorry, is it S? Okay, I'll trust you. And then it is V bar R of K dagger. Now, in one of the classes, we learned how to take the Hermitian conjugate of gamma mu. It was gamma 0, gamma mu, gamma 0. So we then put that in and pull one of the gamma zeros here and write this as a bar. And then we have a gamma mu here. And and over, sorry? Yeah, and over here, there's another gamma 0, right? Hiding in the bar. Under Hermitian conjugate, that gamma 0 moves to the left of V. And there was another gamma 0 here, so those gamma 0 and that gamma 0 becomes 1. So what we have left here is just V. Okay? So this is a neat trick. So by doing this, now we can rewrite this term, this whole term in the following way. So in the next step, what we do is that we take the electron-positron parts, the two factors, and write them next to each other. And we take the muon, anti-muon part and write them next to each other. So we have 1/4 our sum over m squared we have e to the power 4th. And now the electron-positron part. This is just a number times another number. And this whole thing is multiplied by the muon part, muon anti-muon part. And now there's a contraction between this gamma and this gamma, the mu indices. And everything here has prime because they're all outgoing states. Okay. Times the factor that we got from the photon propagator. Now, if I look at the spinor index for this guy, we see something interesting. So for this first part, we have only the sum over R and S. And then now I'm going to write the spinor indices explicitly. So A is our spinor index now. Then we have gamma mu A of B. US has index B. So this is just A, B. All the indices have been contracted here. And we have U bar S of P. C is our new index, spinor index. C and D. VR of K of D. We can then rewrite this in a way such that we get a trace over the indices. So VR of K of A, VR of K of D. So I bring this guy over here because now that I have exposed all their spinor indices, we can move all factors around with impunity, right? Because here's their matrix elements, they're no longer matrices. Of course, there's a sum over all repeated indices, implicit sum. So we just bring the V and V bar next to each other. And then this guy remains in this own place. And then we bar U, we get this U remains here. And this U bar here. And now remember, we had the spin sums where we took the outer product of a spinor and its conjugate, and then summed over the spin labels and used a completeness relationship to replace them by the Dirac wave, the wave operator on momentum space. So these were, let me remind you what these guys were. This was K slash minus ME in this case. And then So if you do this, then this expression becomes k slash minus me d of a, so this whole thing, gamma mu ab p slash plus of me b of c gamma nu c of d, which we can write as trace over k slash minus me gamma mu p slash plus me gamma nu. Okay? So the trace comes from doing the averaging and the on the initial polarization and sum over the final polarizations or spin polarizations, and then using these tricks, right? So next what we'll do is that we are going to say that, well, if our energies are high enough, we can ignore the electron mass. So I'm going to make this approximation to write the final result in a simple form. So if you look at real life values of the mass of the muon and the mass of the electrons, electron is very light. It's just a half of MeV. So mass of the electron is just, well, it's probably, should I just 0.5 MeV, and the mass of the muon is 105 MeV. So we can ignore the electron mass. Then our matrix element becomes, so that object, let me call it X, becomes E4. There is a 1/4 factor, of course, from the averaging, and trace over k slash gamma mu p slash gamma nu. Here we're ignoring the mass term, and the trace of p prime slash gamma mu k prime slash gamma nu minus m squared gamma mu gamma nu. Okay. And then in the tutorial, you proved a trace identity which involved several. Well, there were 2, 4 different slash different number of gamma matrices and traced over, right? So those guys now come in very handy, and you can write this as 4E for P plus K, and I would like you to verify this independently. 2, and inside it's K times P prime, P times K prime, plus 2 K dot K prime, P dot P prime, plus 2 K dot P, mass of the muon. So this is the muon mass squared. So this is our square of the matrix element. So we are going to work out what the differential cross-section for this is in the next 10 minutes. To do that, we are going to choose a reference frame, which would be the center of mass frame. So in that frame, our electron comes in with some 3 momentum p, and our positron comes in some 3 momentum minus of p, which we have written as k in this case, right? So our k is going to be minus of p. And our muons and muon and antimuon go out in this way. So there is some bang here. And this angle, we call it theta. So we are now doing kinematics. So P mu, because we are in the center of mass frame, and we're ignoring the mass of the electron, it should have this form. K mu then should have this form. K prime mu, because it's an elastic scattering, the energy is conserved, and it has some momentum, 3 momentum in some arbitrary direction, K prime. And P prime mu, because we're in the center of mass frame, should have the opposite 3 momentum, where, of course, 3 momentum K mu is the positive square root of this thing. And instead of P plus K, so here it's a 4 moment. These are all 4 momenta. The 4 momenta squared is, we call it S, which is our Mandelstam variable, which we also saw in our tutorial. So these are the quantities that we will use to express our cross-section. So now, using these definitions, we can now work out what all these objects are in terms of things which are like E and K and the 3 vectors, as well as the angle. So I'm not going to write out these expressions. Well, let me write on one, then the others are similar. So, and these are given in the notes, and this is trivial algebra, so you should be able to do it. Although sometimes I run into trouble doing it myself, but anyway, you guys are smarter than me. So let's just write one out. So K dot P prime, for example, is E squared minus K times E times cosine of theta. And there are similar expressions for all the other guys. So when we do this, our matrix element squared becomes, with a little bit of algebra, E4, 1 plus m squared by E squared, 1 minus m squared by E squared, cosine squared of theta. Okay. Now, it's now time for us to plug this into the differential cross-section formula for 2 particles scattering in the center of mass frame, which you saw in Dan's part of the course. So these are all the phase space factors, and then we have 1/4 sum over m squared, which is what we just computed right now.
Sorry.
Yeah?
What is in the first W, that factor? No,
2e.
2e, and then?
1 over v1 minus v2.
Oh, right.
Okay. Right. So the center of mass energy is the total energy of the incoming particle, which is 2 of E. And then we can express V1 and V2. Well, as anyone knows, the velocity of a particle is just its momentum divided by energy in case of the massless electron. And that just becomes 2. Because K and P are same. The modulus of these guys is the same. So anyway, when the dust settles, you have the differential cross-section expressed in terms of a new quantity, alpha squared, which I will define momentarily. So let me make sure the mass is, so this is m mu squared E squared plus, sorry, this is boring, m mu squared E squared times cosine squared of theta. So the alpha is a coupling constant that is customary in describing QED interaction strength, and it's given by the charge squared 4 pi h bar c. In units, so this is dimensionless, so it doesn't matter what unit we are, well, in the units of h1, h bar c is 1. It's given by 1 over 137. So as coupling constants go, it's pretty small. So we can imagine doing some kind of perturbation theory with this coupling constant. If the coupling constants were not so small, then we would not be able to do perturbation theory. In the next course, and also in the course that's coming in late November and December, we'll see that these coupling constant actually depends on what energy scale in which you do the experiment. So this is actually defined at the at a very, very low energy scale. Okay. So now what we can do, we can take the differential cross-section and integrate it over all phase space. Oh, sorry. I'm just going to move over there. And then we can find what the total cross-section is. So the total cross-section is there's a point I'm going to make now. So in the limit in which the hyperrelativistic limit in which the energy of the particle is so much that you can actually ignore the muon mass. So if the energy of the particle is much, much bigger than the muon mass, then your total cross-section is 4 pi alpha squared by 3 center of mass frame. Naive dimensional analysis, if you were doing dimensional analysis, then dimensional analysis will give you this. Now suppose that the matrix element that we computed over here did not depend on energy. It just didn't have any energy dependence. It was given by some dimensional analysis stuff. Our total cross-section would still have an energy dependence because we're integrating over phase space, and phase space still has, energy and momentum dependence. So you can compare how that energy dependence compares to the energy dependence in the real world, where actually our matrix element does have, or our QED computation, our matrix element does have an energy dependence. And then see whether QED is any good. So the result is as follows. So in this axis, you use the differential, the cross section, and multiplied by the energy because this is the ultra relativistic limit, and then of course there's a threshold for this process. If your initial electron and positron did not have energy equal to or greater than the mass of 2 muons, then of course muons will not be produced. And then the phase space result, which is not dependent on quantum field theory, goes something like this. And the QED prediction, something like this. So this is QED, and this is phase space. And can you guess which one do we observe in nature? I'll give you a hint. There was a Nobel Prize given for QED. All right? Okay, so.
Could you repeat the difference between both?
Oh, the difference is that if you assume that your this did not depend on any energy.
What would not depend on the energy?
Maybe or it's just a benchmark of seeing whether you could compare it with some other theory, right?
Yeah.
But it's just a benchmark of saying that maybe QED is not right. Mm-hmm. It's just that all of this phase dependence, all of this just it has some probably energy independent scattering cross section. Matrix element, but the total, because there's a phase space, energy dependence, the final result is still energy dependent, right? You could have something like that. Or, you could compare it with some other theory, which would give you some other prediction.
Okay.
Okay? So, all right, so tomorrow we'll do some examples of Feynman diagrams where the external states have photons. Because we'll see we have to introduce some new machinery there. And also, if time permits, I will do a fun example where we use the gauge symmetry to find the quantization of charge in case a magnetic molecule exists. But that's only if you have time, okay?